Hello, it's Keith here, and this is lesson 49 of the platform-specific series of my Z80 programming tutorials. We were looking at the MSX2 last time and we were going through all the bitmap commands. We didn't finish, so that's what we're going to do again today, more MSX bitmap commands. We looked at the high-speed commands last time, which are very fast for filling, drawing sprites. This time we're going to look at the logical commands, and these allow effects like XORing, transparency, and negation, a negative effect. So we'll see them in action today. So first of all, we're going to do a command called LMMC here. Now, we did HMMC last time, which was copying a sprite from the CPU to the video memory. LMMC does the same, but this time we're allowed to do logical operations. So let's fire it up and see what happens. So we've drawn our chibi character to the screen twice here, but you can see the first time here it's sort of transparent now, and the second time it's kind of backwards. It's a negative of itself. So let's take a look at what we actually did. Now, I am going to assume in today's lesson that you actually watched the last one, because a lot of it's repetitive, and if you didn't, then you're kind of missing out the best stuff. The last lesson's examples are the fast commands. These are the more advanced commands for transparency and things, so you wouldn't want to just do this. So I'll go through things and I'll explain what each command does, but if you missed the last lesson, you're going to want to watch it after you've seen this one. Anyway, so our LMMC test is basically the same as our previous test. The only difference is, in this case, we're running it twice. We are copying data to the screen as before, but the logical operations don't work in bytes, they work in pixels. Now, a 16-color screen has 2 colors per byte, so we've actually had to double up our writing. Before we were sending bytes to the send byte data port, now we're sending colors, and that means we have to do it twice per byte. Once we're only taking effectively the low nibble, and then the second time we're shifting the high nibble to the low one, and we're sending there. And we're now monitoring the wait for TR flag. I said before we didn't need to do that, but with this one I think we really need to, because things are a little slow and a little more complicated for the VDP. So we're waiting for the flag here, and I went over how to do that. This function will do it for you. If you want to see the details of how to do it, look into that please for yourself. So we're running this LMMC generated. The term generated, I mean we're generating the byte data that we want to show, or the pixel data we want to show, and we're using the stack to hold all our temporary values, as I showed you before. So we're selecting a logical operation. Now, the first one was an XOR. XOR is effectively inverting the bits of the color based on the new bits we're drawing over the top. And this is a very simple mode of transparency, because if we draw a sprite to the same position twice, it will clear it and it will not remove anything that was underneath. The disadvantage is that if you draw a sprite over a background with XOR, the pixels that are not black in the background will become some strange weird color, and you see this in some basic games. It's a nice way of getting started, so you don't need to have to worry about redrawing your background, but it is a little bit ugly, so I don't think there's going to be many games that are going to use this really. I think maybe Dizzy did on some of the systems, some of the early Dizzy games. I can't really remember now, but I think they did. So you can get away with it, but it's not ideal. But anyway, that's what we did there for that first one. And then the next one was a NOT, a logical NOT, which inverted the pixels. Our full range of logical operations you can see here. There's implicit, AND, OR, XOR, and NOT here, and these are just our standard logical operations. And then we've got these ones which use the color 0 as a transparent color. Now we are going to see the full range here in the next example to see how they work. Now, as before though, when we run these, what we're doing is we're pushing all our values onto the stack. We are then loading these all into the stack here, loading our stack pointer to HL, and then we're using a long chain of out eyes to push all those values from HL, which is effectively the stack, to the registers we need to, and we need to fill registers 36 onwards for this command. And you can see that just here. We need to fill 36 onwards for LMMC. So that's what we're doing there. Now, LMMC is interesting, but as I said before, I think what you're going to want to do is use HMMC to get your data from your CPU to your video memory, and then do everything in video memory. So you do want to load your sprites into non-visible areas of the screen from Y line 256 onwards, for example, and then use these commands to copy from that. So LMMC I don't think is that useful. What is much more useful is LMMM, which we'll look at in a moment. Now, what we're going to try next, though, is LMCM. This is a bit of an odd command, and one I never used, and I'm not sure you would particularly need to, but we're going to look at it anyway. Now what I'm doing here is I'm putting a pause in, and then we're going to drop back to text screen, and we're going to show the memory of the sprite. Now LMCM copies from video memory into the processor. So we're loading from the processor memory, the CPU memory, into the video memory here, and then we're loading it back into normal memory. So let's have a look at the code of LMCM. So we're specifying the area that we originally wrote our sprite to, and then we're running this command here. We're specifying a range here. We're effectively reading in the range 1 byte at a time here. We're using this getColorByte command, which reads in from the status register 7 here, and that will return 1 pixel of the screen. And we're repeating that for every single byte of our range that we specified just here. Bit confusing, I know, and as I say, I'm not entirely sure what the purpose of this would be. I guess if you were trying to create a graphics program and you were drawing a picture on the screen and then wanted to save that picture to disk or something maybe, but even then you would maybe want to just do it by byte access. But anyway, I wanted to go through all of the commands, even the ones I've never used and possibly don't particularly see the use of. So let's see it working here. So there's our sprite. And now here we've got this memory here. So this is at 8331. This is the sprite as it is in our memory of the program code. So we wrote it into the video memory in bytes, and we read it back out in colors. So each byte here has been split into 2. So this 1 0 here would be this color 1 and this pixel 0 here. And then this 3 0 here has been doubled up to this and this here. And then this 1 0 is this one here. So you can maybe see that it has been read back, but as I say, because we wrote it in bytes but read it back in pixels, we've doubled the amount of data we ended up with. I just wanted to make the point though that it does work. A little bit weird, as I say, it's not a command I can think of many cases you would potentially want to use it for, but I just wanted to show you anyway. This is the much more important one, LTripleM. This is a logical copy, and it's pretty fast, but not as fast as the HMMM command we looked at before, but it can do transparency, and that's why it's important. And I just need to disable into here so that we can see the result. Let's fire it up. So we copied our sprite to video memory here, and then we've copied a tiny strip of it just here, and we've done different operations each time. You can see here we've used this common code here to specify the screen destination Y position and the source here. And we've run this LMMV with this option 90 here, and then we're ORing in the logical operation we selected here. So we're doing all the logical operations. Again, we're setting all of the registers, this time from 32. And you can see the reason for that is that this LMMM does require all of the registers from 32 onwards. It uses a lot of different settings here. Now, what I'm going to do now is, rather than showing you on the physical emulator screen, I'm going to show you this annotated version here. And this shows all of the possible bit settings, because if you remember, the bottom nibble of the command byte is actually the logical operation. So depending on those 4 bits, we will get a different logical operation. The default one is the normal. It's implicit, so it just overwrites anything that was behind it. An AND operation will only set pixels where both of them are set. So we've kind of got this weird pattern here. An OR operation will set if the pixels are set in either the source or the destination. An XOR, not very clear there, but it's actually inverting the pixels that have been overwritten. The NOT is inverting the source position pixels here. And then we've got the transparent options here, and these are really the good ones. So what we're doing with this is we are setting the pixels where the sprite that we're writing to the screen pixels are not 0. If they're 0, we're keeping the background. Otherwise, we're now taking the foreground. And you can see the effect when we're doing this inverted one, because these pixels were 0. So they're now being left alone, and we've lost that white effect here, because this was the pixel 0 being changed to pixel 15 here, the maximum color. So you can see we've been able to have this transparency effect, and I think it's this T implicit one that you're probably going to want to use for your transparent sprites here. Anyway, I just wanted to sort of give you a demonstration of all of the options here, so you can try them all out. And as I say, you can see them all here, and it's going to be very easy for you to switch between operations if you use these definitions here. Okay, so that's the logical copy. We've also got a logical fill, virtually the same. We looked at our regular fill last time. The fill is much faster than sprite copying, and I've not tested it, but I assume this one's faster as well. But it is going to be slower if you don't need the effect. But maybe you want to make part of your screen invert, and so of course you can do that here. You can see I've done a couple of fills here. So you can just see just here, we've got this LMMC test here, and we're just doing an implicit fill and an XOR here. We're specifying an X destination, a Y destination, and a height and a width, and a color to fill in. We're only setting one nibble because these all work by pixels, so rather than setting FF like before, we can just set 0F here, and it will fill it all in white. The command itself is just here. We're loading our logical operation into the low nibble of the command byte. The top command byte is 8 here. And then we're pushing these all on the stack, and we're setting from registers 36 as before. We often set from 36, and that's why I say you could actually use these same functions for many of the same commands if you were looking to save memory. Let's try this line command. Now this is quite a curious one because most of the commands we've looked at the moment have been about bulk filling. But this line one is a little bit odd. Let's fire it up and let's see. So I guess this will be if you're using your graphics package. I guess it would probably be worth looking at if you were trying to do some kind of vector game as well. So you can see we've drawn 3 lines here. Let's take a look at the code because it's a bit surprising. At least it was surprising to me. Now we're using the X and Y position for our destination. We're loading those into IX and YY here. And we're specifying NX and NY. But these aren't actually a width and a height of the line. They're a long side and a short side. And then as part of our direction, which we're loading into B here, this was before the direction we were drawing our sprite or copying our sprite and things. And as I said before, if the destination overlaps the source, we had to make sure that was correct. But now it's actually changing the direction of the line. So if you look here, we drew this white line and we set down and right, so that went that direction as you'd expect. But these two both went down and left, and if you look, the long side and short side settings are the same, but they've gone in different directions. And that's because if we set the bottom bit to either 0 or 1, we will actually flip which direction is the major axis. So this one and this one are the same settings, just with that flipped. That's the way it works. Seems very strange to me, but there you go. As I say, I never used this, and I couldn't immediately think of a reason I would spontaneously decide to, but if you want to, that's the way it's going to work. So again, we're just pushing all of these values onto the stack again, setting from register 36 with a load of out-I commands. That's our line command. That's what it does. I'm sure it'd be very useful if you needed that. So now we're going to try a pset command. We can set an individual pixel, just one pixel. Seems a bit anticlimactic after all the things we've done, but as I said before, we're going over every command, so let's see it in action. So you got 2 pixels here. You saw I was flashing the green one and I had the other one constant. Let's see what I was doing there. So this is a logical operation again. So the first pixel I was setting to implicit, so no matter how many times I wrote it, it didn't change. The second one I was XORing, and as I said before, if you write twice with XOR, you will undo the first operation. So I was effectively making the pixel flash there. So I had my pset via stack command here. Again, working from register 36, just writing all of these values, although a couple are unused here, to the stack, and then using that stack as the source for the out-I command. And that's all we need to do to set pixels on the screen. I don't think you're going to want to do very many. I think this is going to be quite slow. You would want to go to some faster way of doing things if you needed to set a lot of pixels. But again, maybe you're doing a graphics package or something that this is appropriate. So that's what you can do. Now we're going to leave this pset routine running, and now we're going to use the point test. Now the point command, you may be familiar with it in BASIC, is a test of a pixel. So let's run it now. So as before, we're flashing our green pixel with that XOR. And now we're back to the text mode. And you can see here we've got an OF and an O2. So we want to see what our code was doing to work out what that means. Now those are the values that were in BC when this returned. And what we did is we ran this point command and we were specifying an X and a Y position. Now I'm wasting a lot of values here. And as I say, this is the only real point where maybe you would want to write a different version that set the indirect register a second time to point to 45 and then just write a single individual byte. But just for simplicity, I'm just pushing some values onto the stack, even though we don't really need them in this case. So what we're doing is we're waiting for the CE flag, running the VDP point command, which is just a big load of out eyes again. And then we are restoring our stack here, and then we're waiting for the CE flag again to check this command has finished. Then we're getting the color byte, which is register 7. We just need to read in from that, and that will be the pixel that we read. So what pixels did we read? Well, we read 120 and 128. And if we look at our pset command, where is it? You can see we wrote color 0F and color 02 in that pset command. And what colors did we read back? 0F and 02. So you can see that we were successfully able to read back the pixels we set. I can even prove that to you if I just disable that. You can see it's now 0F, 0D because I didn't clear that pixel that time. So there we go. That's the point command. Again, that would probably be quite handy if you were doing a graphics package. I don't think you're going to need it for games though. The next command we're going to look at is a quite tricky one, a search command. This allows us to search the same line for the state of a pixel. Again, I think there's very little purpose for this for gaming, but I think you would probably want this if you were trying to create a flood fill command in a graphics program. But let's try it out. We've tried out everything else, so here we go. So what we're going to do here is we're going to scan across the line and we're going to look for the pixel we're plotting here. And you can see we've got the result FE78. Let's see that command and see what it did. So we're reading the Y line 120 here, and we're looking for the pixel F here, which is color 15, the white pixel. And we're setting the search to be the pixel equals F15, and we're searching to the right. We have a couple of options, you see. We can search for the pixel that equals the color we specify or doesn't equal the color we specify. And if you were doing a fill, you would probably want to fill the line up to the color of the current pixel. So you'd probably want to say, well, the current pixel I've been clicked on is color 0, so I want to find the first color that isn't 0, and then you'd want to fill to that point, something like that. But you can search either to the right of the specified start point or the left. So what we did is we searched from pixel 0 on line 120, and line 120 is where we drew our white pixel before in the pset test. So we drew that pixel at 120, and what's our result back? FE78. Now this result actually returns 2 bytes, but all of the unused bits are 1. So effectively the FE bit here, it can be ignored. The result is 78. So if I get my hex calculator up here and write 78, and then I convert that to decimal, you can see we found pixel 120, which is the one we set in our pset test. Now, how do we return it? Well, it's a bit tricky, as you can see. We first need to wait for the CE flag to check that the search is completed. Then we're just restoring our stack here. We're setting a result of 0 if it didn't complete. Then we want to check this bit here of the status register, register 2. And we want to check this BD, which I think maybe stands for border detect. I'm not sure. I don't know quite why that is relating to finding colors, but that's the way it works. Anyway, this will return a 0 if the color's not found. So if it's not found, we jump down here. But if it was found, then we read from status registers 8 and 9 here. And we're storing that into C and B to return a pair that will match the pixel that was found. Now, again, I can prove to you that that was really working. If I disable my pset test here and run the example again, you can see now that the return value is 0 because there was no pixel on the line we searched, so we didn't find it. Okay. There's just one last command we're going to cover. I should move this down here for a bit clearer ordering, and that should really be at the top for the way we covered things today. So the last command we're going to cover is the stop command. Let's see the code. So what we're doing here is we're setting a fill command. We're starting the fill command, we've got a little pause, and then we're sending a stop command. Now the stop command just uses a single register 46 here, and we just set it to 0. So I've been pretty wasteful up till now with filling registers that aren't needed, but even I have a limit. I'm not going to fill all the registers from 32 for that. So we're just setting a 0 directly without using the indirect registers there. So we're just setting that to 0, and that will stop the command. So the fill will start, there'll be the CPU pause, and then the fill will be told to stop. So this is set to fill the entire screen white. Let's see what actually happens. So we filled just a few lines here, and that was the amount of time the pause took to run, and then it stopped. And that's because the CPU was told it to stop. Now, of course, if this is going to be useful, if you actually are writing something where you're sending VDP commands and the new command needs to happen, but the CPU was busy with the last one and maybe the last one's no longer relevant. Maybe you were drawing the background and the player's just died or something. Who knows? Now, you can see there without the delay, I think maybe it's just filled that tiny little bit there. But the VDP is pretty fast. It's not amazingly fast, but it is pretty fast. If you want to see amazingly fast, you want to look at the V990, which has these very similar commands, at least a few of them. And they're virtually the same, but it's extremely fast. So if you like what you're seeing today, but in your own work you find, well, I love these commands, but I can't make my game with these slow commands, look at the V9K, which is supported by Open MSX, and so you can write your game with that VDP, with that V9K, and it will be really nice and smooth, but it'll be just as easy as working with these commands. Anyway, that's the last of the commands I wanted to cover today. Let's say we've got the summary table here. I hope you found this interesting. I know this was a very quick way of going through them, but they are very complicated, and if I'd gone through it in any more detail, this would have ended up an extremely long lesson that really no one would watch. If you're interested in this, you want to download the official documentation and then maybe go through it in a bit more detail. But if you just want to have a go with the commands, hopefully my source code that I've shown you today will help you out. If I find any mistakes in today's examples, I'll improve the source code to represent it. It was written relatively quickly, and as I say, most of these I'd never used before myself until I wrote this tutorial. Anyway, I hope you found this interesting. We've still got a little bit more MSX to do. I'm going to cover the more advanced modes of the MSX, the 256 color mode, the high-res modes, and also the true color modes, if you could call them that, the YJK modes of the MSX2 Plus. So if you like your MSX graphics and you want to see some more advanced stuff, please like and subscribe, and you'll see those coming very soon. Thanks for watching today, and goodbye.